Hello, Math 1224. This is Dr. P with the last lesson launch of the semester. Wow. Feels like we just started yesterday. I'm sure it doesn't feel like that to you. You've been working really hard. Anyway, this is lesson launch 23.2, Truth Decay. Figured I should get one more pun in there. Anyway, the picture you see here probably gives you a clue about what it is we're going to talk about in this video. So I have to say, I thought about making this video just a short follow-up to the previous video and having it be like a quick exponential decay model type of problem. And then I realized, this is the last lesson launch video. Let's do something fun. Okay? So I want you to imagine there's this town called Valville. And there's some population there, but we don't know what the population is. It's just some unknown constant p. Okay, we are going to assume for purposes of this problem, the population of the town doesn't change over time, because the time we're going to be talking about just a matter of days. It's not going to be years or months, just days. So I want you to imagine somebody from outside the town, like a magazine, you know, like the National Enquirer type of magazine, you know, the kind that's not worth much of anything, starts a rumor. Now, in real life, goodness knows, nobody would actually do this. No reputable news publication would start a rumor just for the sake of riling people up. That would be a silly thing to do. But let's say for the sake of this story that the American gossip rag starts a rumor. Let's say, just for the sake of the story here, I'm trying to find my purple color. There we go. Starts a rumor that, actually, let me make this orange now that I think about it. Sorry, I'm very picky about colors today. Starts a rumor that that Half-Life 3 has finally scheduled a release date. Okay, for those of you who don't spend all of your days on the internet, Half-Life 3 is a much anticipated game from Valve, hence the Valville, that people have been waiting for years, and people have been waiting for some announcement of when Half-Life 3 is going to come out. And probably because nobody actually plans to make the darn thing, there's never been a real announcement, but people always expect that there will be one. So anyway, let's say that American Gossip Rag starts a rumor that Half-Life 3 is coming out, and they know when it's going to come out. Okay? So what we're going to do in this problem is we're going to keep track of the number of people in the town who are aware of this rumor. So let's let x of t be the number of people in the town aware of the rumor t days after the rumor starts. So maybe what happens here is the magazine comes out, some people read it immediately, and then after that, other people get hold of the magazine, maybe because they've heard about it or something. All right? So in this problem, what I'm going to do is I'm going to set a few values, and we're going to try and figure out what the underlying model is here. So the values I'm going to set are, let's say that x of 0, let's say we know that that's, good Lord, my handwriting is not so good today. X of 0 is 1,400. 1,400 people know of the rumor straight away. And then x of 6, after 6 days, the number of people aware of the rumor is 7,100. And then let's say x of 12 is 8,525. Sort of random numbers that I'd picked out. Okay. So we're going to try and figure out what the function x of t is. What is x of t? All right? So I just want to think about what in the world kind of natural law might govern this phenomenon. Because rumors spread in a number of ways, and what kind of model we're going to use depends on how the rumor spreads. So let me go back up here to this handy visual that I have. So we're assuming, for the sake of this problem, that people are getting this information from the American Gossip Rag. That's where the info comes from. So over time, this gossip rag infects some number of people, and there are some people who are initially aware of the rumor, and then over time, there's this set of people who are so far uninfected by the rumor. Okay, so I'm going to draw a little box around them. So this is the set of people uninfected, and on any given day, just for example, on any given day, a few of these people, some fraction of these people, are going to get infected by seeing this publication. Okay, and those people will become infected. So they now leave the pool of uninfected people and join the pool of infected people. And in the meantime, the number of uninfected people shrinks to a smaller amount. But the assumption I'm going to make is that every day, some fraction of the people who don't yet know the rumor become aware of the rumor. Okay, so just to be clear, these numbers down here, these ones down here, These are the number of people who are aware of the rumor at any given time. So I'm not saying that on day 6, 7,100 new people become aware. I'm saying by day 6, 7,100 people are aware, including the 1,400 who were already there. All right, clear as mud. Okay, so anyway, so what should be the fundamental assumption here? I have a population of P. I don't know what P is. I'm just going to treat it as an unknown constant right now. But what it sounds like is the rate of change at which people become aware of the rumor is proportional to how many uninfected people there are. As time goes by, and you kind of see this with the numbers that I put here, the spread of the rumor seems to slow down after a while because the number of unaware people shrinks. So it seems like at any given time, the rate of change of awareness of the rumor, if you will, is proportional to the size of the remaining uninfected population. So it's proportional to this chunk of people. Okay, well, if this set of people is what we're calling x of t, that is the number of people who are aware is x of t, then that means that this group of people here, the number of people uninfected, is p minus x. So it sounds to me like what that means is that the rate of change of the number of aware people is going to be proportional by some unknown proportionality constant to the difference between this unknown population and the number of infected people. So remember, this tells us the number of uninfected people. All right, so far so good. So if you didn't like a problem where we had 2 unknown constants, here's a problem where we have 3 unknown constants. We're going to try and solve that. Okay, so I have some data points. I think at this point the best thing to do is try and solve this differential equation in general, and then we're going to use formula fitting, as we did in the last video, try and find all these unknown parameters here, okay? So let's see here. So what does solving this differential equation look like? Actually, that part is not so bad. I'm going to use separation of variables, divide by p minus x on both sides, multiply by dt on both sides. Make that a clear k there, okay? And then integrate both sides. So I just keep going here. Integrate both sides. Get the integral of k dt. So that means, now I have to think about this a little bit. The antiderivative of 1 over p minus x. P is a constant, but that x, remember, that has a coefficient of -1 on it. So I think that's going to give me a negative natural log absolute value p minus x. That negative is there due to the chain rule, because I've got a negative coefficient on x here. That's going to be equal to kt plus c. All right? So if I manage that a little bit using algebra, first of all, p minus x, if x is the number of people who know the rumor, then this quantity here always going to be greater than 0 because, well, it's greater than or equal to 0, I suppose. You'll never have a negative number of people who don't know the rumor. So I believe I can drop that absolute value and just say natural log of p minus x is equal to negative kt minus c. I just move the negative sign over to the other side. So now, if I exponentiate both sides, just stick a big old e under there. Now I'm breaking my own edict against doing both of these steps at once, but I'm just running out of space here. I feel like, even though in theory I think explaining everything gives you infinite space, I feel like sparing the space. Anyway, p minus x is going to be equal to e to the negative kt times e to the minus c. And again, e to the minus c is just a fancy name for a constant multiplier. So I've got some constant here times e to the negative kt. All right. Now, let's see here. I'm trying to figure out what x of t would be. So I think that what's going to happen is if I subtract p from both sides, I get negative x equals a e to the negative kt minus p. And then if I multiply both sides by -1, I get x of t equals p minus a e to the negative kt. All right. You might say that this formula over here is packed with excitement. No? Okay, never mind. Sorry. Anyway, let's just think about how that might make sense. So we've got the population of the town here, and we're subtracting from it this amount, which if you recognize what this is doing, this exponent is becoming more and more negative over time. So that means this term here is decaying. this term here is shrinking towards 0 as t progresses. So what that means is that the value of this whole expression should be moving towards p, which kind of makes sense. If people have constant exposure to the rumor and nobody has any escape from it, which I don't know about you, but I never feel like I have any escape from stupid celebrity rumors, then the number of people aware of the rumor should creep towards p over time. But what that doesn't do is it doesn't tell us what the values of these missing parameters are. So I'm going to take that and I'm going to move it upstairs so that we can play with this some more using the data that we were given. Okay, so remember, x of t equals p minus a e to the negative kt, where p is some constant, which we're ardently interested in finding out, a is some constant, and k is some constant. Okay, off we go. So back up we go to the top of there we are. So let me just rewrite the model. The general model is x of t equals p minus a e to the negative kt. All right, we're going to try and resolve the values of all these different coefficients here. All right, now at some point I may just break away and use Wolfram alpha to solve a system of equations or something, which you could do just as well on your own. But let's see what sense we can make of this. All right, so let's start with x of 0, because having t equals 0 is usually kind of a nice situation to have. So x of 0 is 1400, and at that time the right side of the equation is p minus a e to the minus kt. So let's see, a is just a, we don't know what a is yet. And then when t is 0, e to the minus kt is just 1. So I think that p minus a has to be 1400. And then when x is 6, I've got 7100 on this side. I still have this term of p here. And now I'm subtracting a times e to the minus 6k, because t is 6. And then when t is 12, I've got 8525, weird random number there, equals p minus a e to the negative 12k. So I think that's what I have so far. And now it's just a matter of figuring out how in the world am I going to solve this system of equations here. So what I'm going to do here is I'm going to do a little bit of strategic tinkering around. I thought about this for a bit. And I think that what I'm going to do is I'm going to label these equations 1, 2, and 3. Sorry about that 2 there. It's kind of gross looking. I'm going to subtract 2 minus 1. And, good lord, this is worth trying to salvage here. Okay, like I said, 2 minus 1. That's going to give me, what does that give me? Let's see, different color here. That'll give me 5700, I think. 5700 equals a minus a e to the negative 6k. So that's nice. I've managed to eliminate one of those variables, p, one of those unknowns. So that's good. And what if I calculate equation 3 minus equation 1? Now this is kind of a shot in the dark about what might be useful here. But I think that's going to give me 7125 equals a minus a e to the negative 12k. Okay, so that's kind of nice. And then, well, let's see here. What else could I do? I could at this point try, well, actually there's a couple of things I could do. One thing is I could factor in both equations, because both equations on the right side have a common factor of a. So I get 5700 equals, really, now if it's a system of linear equations, I feel like we all kind of know what to do, right? But, you know, bring in all this exponential stuff and it's like all bets are off. It's just savagery out there. Okay. So I get 5700 equals a times 1 minus e to the negative 6k. I'm going to call that equation 4. And then 7125 is a times 1 minus e to the negative 12k. All right. And then I'll call that equation 5. Now, what happens if I divide equation 5 by equation 4? Just see what happens. That'll get rid of that a. That would be nice. And then I'll have something that's entirely in terms of k, which sounds pretty good at this point, actually. So if I divide 5 by 4, then I get 7125 over 5700 is equal to 1 minus e to the negative 12k over 1 minus e to the negative 6k. All right. So now I think I'm in a position where I can solve for k. And to do this, I'm actually just going to go over to Wolfram alpha And I'm just going to type this equation into Wolfram Alpha and ask it to solve for k. I know that it probably would feel better if we could do all this by hand, but honestly, I don't think you want to go through, or I don't think you want to see me go through that whole process. And with something this complicated, I actually want you to use technology. I don't want you to sit around for 30 minutes trying to figure out how to solve this whole thing by hand. So when I punch this into Wolfram Alpha gives me k approximately equal to, and it's very close. I mean, it's not exact, but it's quite close. K equals 0.231. So that's one of my missing parameters. And now I think I can just wind my way backwards through these other equations. I think I'll use this one to try and solve for A. And then once I have A and K, I bet I could use one of these ones up here to solve for P. Actually, I'll probably use equation 1. That one struck me as the simplest. Okay, so anyway, so what happens next? So I had equation 4 told me that 5700 was equal to A times 1 minus e to the negative 6k. All right. If I punch in 0.231 into that equation there, I'm going to get, let's see, 5700. So what is A? A is equal to, 5700 over 1 minus e to the negative 6 times 0.231. Is that right? Yeah. So 5700 over 1 minus e to the negative 6 times, now I'm just punching into Cortana again. I have no shame. It looks like I'm going to get A equals 7600. So I get A equals 7600. So that's another of my missing parameters there. And now you'll be delighted to know the last part is not too bad. I go back to my original equation. So A was 7600. Okay, this is not an exponent, it's just saying A is 7600. So if you look at that equation, P minus 7600 is 1400. 9,000. Hooray. So now I think I know that my model for the spread of this rumor can be specified down to the following. The number of people aware of the rumor T days after the introduction of the rumor is 9,000 minus 7,600 e to the negative 0.231 t. Okay, you have to admit, it's kind of cool that you can do that, just based on, I mean, heck, I didn't even know the population of the town to start out with. Now I know exactly what it is. It's just 9,000. I don't know, it's kind of cool that you can find that information, assuming that the model holds up. Okay, so one more thing I wanted to mention about this. I realize I'm like in super long video territory now, not the longest I've ever done. But I want to talk about something else. I want to sort of flip this problem on its head, and rather than think about the number of people who have heard the rumor, I want to focus on the number of people who haven't heard the rumor. Because that's actually kind of a straightforward decay model. So how many haven't heard the rumor? Let's call that y of t. Number of people who haven't heard the rumor. And if you think about how x of t was built, x of t was just the population minus this other number here. So if you want to know how many people haven't heard the rumor, it's just going to be the population minus this whole thing here. It's going to be minus population minus all this, and the population was 9,000. So that means that the number of people who haven't heard the rumor, who are uninfected at time t, is just 7,600 times e to the negative 0.231 t. And that is actually a straightforward exponential decay situation. Now, I kind of buried it under some other mathematics here, but we could have just done the entire problem by thinking about the number of uninfected rather than the number of infected. I guess the obstacle would have been we wouldn't have known any specific data points for how many uninfected because we didn't know the population of the town. But in retrospect, the model is actually a lot simpler than it initially looks. But one thing I want to mention about this is that there are different ways of thinking about decay. One way of thinking about decay is to think about how long it takes. I'm going to write this down. How long does it take? How long before this quantity, I mean the whole thing, the number of uninfected people drops to half of its previous value? So how long before that quantity gets cut in half? We could actually solve that. So we could say, how long does it take before this number of people drops to half of its initial value? Well, the initial value is 7,600. because when t is 0, that's what we get for y of 0. So the question is, how long does it take before the number of uninfected people is half of 7,600? So to find out, we need to figure out when it is that e to the negative 0.231t is equal to 1/2. You may have done this problem before in Algebra 2 if you had a really good unit on exponential functions. This means that negative 0.231t should equal the natural log of 1/2. And that may make you panic a little bit because it looks like we've got a negative number on the left side, and it looks like t might be negative, but in fact, natural log of 1/2, that's a negative number. So everything's going to turn out just fine. I'm going to calculate t equal to the natural log of 1/2, divide that by negative 0.231, and what do I get? I get 3. So it takes 3 years for the number of uninfected people to get cut in half. That means we could say that the half-life of unaware people, which is often called lambda, is 3. Oh, wait a minute. You know what that means, right? That means half-life 3 is confirmed. Haha. Okay, well I was expecting a bigger payoff out of all that, honestly. But anyway, I just wanted to show you that this is something you can calculate if you're given an exponential decay model. You can calculate the half-life of that by thinking about how long it is before whatever it is you're measuring gets cut in half. Anyway, so there you go. There you have it, the official announcement of Half-Life 3. And it's embedded in this beautiful video about how to construct and solve an exponential decay, or sometimes people would call it an infection model. And anyway, that's the, oh, wait a minute. Oh, crap. Well, it looks like that was also just another issue of the American Gossip Rag. Well, anyway, so that's it for the videos. That's the last one I'm going to do this semester. For those of you who watch them faithfully, I appreciate your diligence in keeping up with these, and I hope that it helped your learning. I know that I learned quite a bit about how to make these. I obviously did not learn how to make them short. Maybe I'll figure that out next semester, but I felt that this would be a fun opportunity to spend an extended amount of time working out one more challenging example. So anyway, thanks again, and I will see you in class.